Um, raw data. So you should be able to my point here is for you to understand how and have the resources to, if somebody was to give you raw sequence from a machine, how you would process it to do what you're doing with data today and tomorrow. Okay? So as I kind of pointed out, we keep all of our data, in a FASTQ file. Now I'm just talking about what we do in lab. If we have a FASTQ file at a sequencing facility, say if it was somebody else's lab, I'm comfortable that you could be able to curl that and bring it to your machine. So the first step, after the sequencer calls and says, "Hello, I have your sequence. What do you want me to do with it?" You say, "Give me a URL, give me an HTTP address, and I will curl it and put it on my computer and start." Okay, so that's all what this is. Of course, yes, you could hand them the drive and they could plug it into, but I'm just trying to show you what we do. Okay, this is important to a lot of you because you've asked me to go over it again. So if something doesn't make sense, just raise your hand or just yell out a question. Okay. This could be considered, might be considered, a little bit worrisome. But the next thing we do is make sure that when we download that data, that we didn't lose some bits in the internet pipes. Okay, and this is what we call is getting a finger. I want a fingerprint of that file or MD5 hash when it was at the sequencing facility, and then I want to check that fingerprint after I download it, and those fingerprints need to match. Okay, so that's checking the data integrity. All right. Again, you don't want to spend a week working on a data or a month working on a data set and find out that halfway through the download, it broke and you only analyzed half of your data. You'd say, "I don't worry about that. I had a Jupyter notebook. I just changed the file name." Okay, so in this particular case, what I'm doing is I'm running the program to get that fingerprint on these files I downloaded. So again, you should be comfortable with running any program now in the command line or Jupyter. Something simple like in this particular case, all you put is the program. You don't even have to have flags. You just say file location, file location, file location, file location. And then instead of looking at the output, I'm saving the output. Okay? And now I'm doing a head on that file and I'm looking at it. So this is the program that makes the fingerprints. These are the fingerprints or hashes. Okay? I explain what that means. I'm also going to do the hash, or actually, if it was a good sequencing facility, and you might have seen this when you downloaded BLAST. I think all the BLAST files had an MD5 file associated with it. That was the fingerprint of the program. So if you were downloading the program, you could see if you did it. But in the sequencing facility, it's going to have a MD5 file. This is the one that after I downloaded, and they're the same. Okay? And then yesterday, I showed you, I just used another program that's just built into Bash. These are just Bash commands. Diff. Okay, so I said, I want to look at the difference between my fingerprint file from after download, fingerprint file before download. I do not get any output because there are no differences. If there were differences, it would have told me exactly what the differences were. Okay? Okay. There's two ways you could go now. Doesn't matter what kind of order. Okay. Yesterday, I showed you trim, then quality lookup. Now let's just say, another order you might do it is, I have good data. I have a good fingerprint. First thing, let's run it through quality control. That might be a more logical step of what you would do. I want to visually see the quality of it now that I know that I've downloaded it right. Okay. So if I was to do that again, I'm going to use a program. This will probably be recommended. It's an open source one. It's called FastQC. Okay. All right. To run this program at the command line, you just type install FastQC and then the files you want to do quality check on. Okay. I also showed you that you can do this in Galaxy, and I also showed you could do this in iPlan. So those are both cloud services. You can download that software, and it actually has a GUI interface too, a push button interface too. So if you just want to Google FastQC, you can download that. So it's not downloaded on these Windows machines, but that's the program I recommend. I would recommend doing it from the command line, but it does give a nice, pretty output. Okay. If you run it to the command line, it takes a long time because it's looking at hundreds of millions of sequences. And then if you run it at the command line, what happens when you're done? So this is a screenshot of my computer. After I ran that, it created all of these files. Okay. So it created HTML pages, zipped up of everything. And these are just pictures so that if I clicked on this HTML, it's local, it looks like a web page. That's what that means. So after when it runs, it creates an HTML file that has pretty pictures that helps you visualize the quality of your data. And this is what it looks like. When you open up that HTML page, this is exactly what it's going to look like. We're going to have a nice summary here, but it's easy to see green and red. Again, there's no totally right or wrong, but I will tell you what I'm looking for. The first thing is the base sequence quality. It would be very nice for this all to be in the green region. Okay, that means it's pretty high quality. It also gives you a nice summary of the sequence length and how many sequences are. So there's 200 million just in this one. Okay, is that right? Is that the right number? Okay. It would be very hard to look at those one at a time. Okay, this is the other one that I like to look at, and I showed you yesterday. This looks at the per base sequence content. If you look at 200 million sequences and average them together, you're roughly going to see the same contributions of A, C's, and T's and G's. Okay? Roughly. Okay? And there's always going to be a little bit more A's and T's and C's and G's. This is an abnormality. What this is indicative of is there's an adapter there. Okay? Does that make sense? There's a large proportion of the sequences is the actual exact same sequence. And for example, in position 7 is T. So this is the key to me that there's a unique signature here that's not real, it's not biological. So I'm going to want to, in my case, I'm going to just cut this. Okay? Most trimming software would also, by default, clean this up, okay? Depending on what the default conditions are. If this is going down in the red, okay? If I run it through a trimming software, it would remove all of that. So it does. That's why I say it logically makes sense to look at it first, right when you get it, then run it through trimming, and then look at it again, and it should look better. Okay. The other things it does is it tells you overrepresented sequences. Okay, Fast QC does. Just by itself, it has the lumen adapter built in, and in fact, there's a lot of lumen adapters, and that's probably what we were seeing there in the picture. So you can visually see it, and then list them out for you. Okay? So there's 1 million times it found this sequence. It's the index number 9. It's there, so we want to get rid of it. Okay? So again, I'm going to use a program. It's going to be something I can run from the command line. You should feel confident and comfortable. You put the program. Put your flags. If you don't know what the arguments are, you type help. It will tell you. In my particular, so this might look a little weird to you because I'm putting out the full path of the program on my computer. If you install it correctly, you won't have to, well, I don't want to get too confusing, but if it's in the path of your computer and it knows where to look, you don't have to tell it where it is. But some programs, I just put the full path. Okay? Meaning you could get in there and manipulate the system to tell it where it is. But this is where the application is on line machine. I'm telling it it's paired. I'm telling it to clip 14 base pairs because I decided 14 base pairs looked like an adapter to me. Actually, it was like 12, but I said, let's just be safe and cut an extra more. It's going to cut the adapters built in. The file that has all the adapters in it is located here. Okay, so if I wanted to look at that file, pad it or head it, you can see all the adapters. Okay. Then I just select the files, and then it runs for a long time. Yes.
You're going to cut 14 bases plus making the program
Yes. That might be redundant. That's a good point. So I could maybe not do that.
But can't hurt.
Right.
Can't hurt.
But a good what would catch that is when you looked at it the next time around, and if somehow that made it cut 30 base pairs, maybe I go back and do it again. But excellent point. So this tells you what it's doing, what it's finding, and this just gives you all the output. That was nice because it stays in your notebook. Does it to a lot of files. And now I'm showing you a screenshot of what happens after that runs, which might be a very long time. It gives you a report in a text version. It gives you these validated. So this would be the post-clean data. So each one of those, that's the one end and that's the other end. Okay, it reads 30 gigs. And I told it by default, it actually kept the unpaired matches. Remember, it's paired in. If I wanted those, I could include those for later analysis, but they're only about a few hundred megabytes, so I'm not even going to deal with them. I've got plenty of data to do it. Okay. All right. So that's what created on my computer. So these, in theory, are my new working files that I hope are cleaner than they were before. And then I'm going to run Fast QC again. I'm going to run it on these new files that have been validated. It's going to run, and then I'm going to look at the picture. Okay? Does that make sense? If I'm happy with it, meaning that the squiggly lines are gone, and no adapters, then I'm ready to go to the next step. Okay? Any questions? So these are your files. What are you going to do with those? Next, if you're happy with the visual output, in this particular case, assembly. So again, you should be very comfortable with this. And at the command line, you would just type !Trinity.Perl once it's installed on your computer, if it is. And then I probably have no idea what the commands are. So the first thing I was going to do is type help, or go to the website to the people who make the software and read the manual. They will also tell you exactly what to do. But I can tell you right now that the minimal settings are going to be, they want you to tell you what kind of file it is. If this is a FASTQ file, you can set the memory. So this is the Java memory. You would want to set it as high as you could. My machine has 24 gigs of RAM. So I say use it all. I tell it where the two files are, the left one and the right one. Again, that's the paired in, what that means. And then I can tell it how many CPUs have. My machine that I was running this on, which is much bigger than a laptop, had 18, so I didn't want to push it to the limit. But 2 free in case somebody wanted to check their email, and run that. And so on average, something like this might take, I think the data you're working with on this machine took about 5 to 6 days, okay, to work to actually get a result. Again, remember, what did I say this was? 200 million reads that it had to deal with, okay? All right, and so at the end, when this is done, it's going to, let me show you what it creates, okay? Okay, so if you want to get real personal, this was running on like an one blade of an Xserve Apple server, and I had it write out directly to one of our web-facing NAS servers, and these are all the files that it spits out. Okay, if you read the manual, it goes through different categories, different processes within Trinity called jellyfish, inchworm, okay? Bowtie is a program that it uses that you might have heard me mention earlier. That's what actually does the assembly. You could easily just use Bowtie if you were doing a genome assembly. Trinity obviously takes consideration that you have genes. Okay, not obviously, but it does. And again, so this is everything it spits out. Those files are big. This is the exact file that we're dealing with. Okay. Again, everything's on a web-facing server. So if I go to Mexico and need to show it, I can just go pull up the web address and get it. So that's what the results look like. And actually, within Trinity, you can run a program called transdecoder. And what that does is that again, just command line, but that's the output from it. It does the deduced amino acids. So remember this morning, I thought I was being really smart and just taking the longest open reading frame and doing all that, like 6 or 7 steps. Trinity will actually do that with just a command. Okay? The most likely deduced amino acids.
reference from the beginning, and then you're gonna
Say that again.
that sequence of amino acids
Uh-huh.
is considered to be the most probable.
Most probable longest version of the gene. Yes. I'd have to look at. So this is my actual lab notebook. Again, this is some of the output that Trinity gives you. So you get a nice. If you were to open up one of those text files in the summary, you get the number of genes, transcripts, and the longest isoform. So Trinity does both the gene and the different transcripts. Gives you the median length, the average contig length, the assembled bases, and then in order to get the this just shows you that, I mean, all I did to get to run the transcoder is run this code, which is just transcoder. It's only one line, so it's harder to see, but I just tell it where the file is. So I just told it where the output file was in Trinity, which is trinity.fasta, and then it provided that protein file that I showed you. And then, of course, what I did afterwards is take that protein sequence and blast it, and this should look very familiar with what you've been doing today. I did a protein blast of this transdecoder translation of the GUI duct. This is the database I use, Pro, everybody's favorite. Z-value, max target seeks. This is an interesting thing Miguel found earlier. If you're familiar with BLAST, this tells you that there can be, you only want one match for your sequence. In actuality, the way BLAST works, it can match one sequence, but it can match it in two different places. Okay, so he noticed that he was getting multiple hits or multiple lines, right, per your query. Okay. In this large volume, we don't really care if it goes 2 or 3 times. We just want the top hit. And so Max HSPS says, okay, just the best place in one sequence. Okay. Yeah, I want to say it's the hits. I forget what it stands for. Hit score something, but it's in the manual. Output. And this is the other fun one that you don't really have the ability to play with. Say you have 16 CPUs or 18 CPUs on your computer, you could say, use all 24 of my cores to do that, and it does it 24 times faster, okay, than it would. This is really CPU intensive. The BLAST assembly is very memory intensive. So if you that's going to be probably your limiting function as you get more and more data trying to assemble hundreds and hundreds of millions of readers, is having access to a computer with a lot of memory. You can use things. You can spin up Amazon instances and rent a machine for a short period of time, because now you're comfortable with Linux. You could get in there and it would be just like this. You could use possibly something like iPlant too, where you need access for supercomputers. Okay? But if you have a machine with 24 gigs, or I'm sure bigger than that, it would work fine. All right? And then my notebook is the output of the BLAST too. Okay. So are there any questions? Does everybody feel comfortable that if somebody called them up and said, your sequence is ready, you would at least know how to get started? What would be the first thing you would say on the phone? Give me the URL, if you probably speak Spanish. Give me the URL, and then you're off. You're curling, you're MD5ing it, then you're fast QCing it, then you're trimming it, then you're fast QCing it. Again, and if you're happy, then you're running it through Trinity, blah, 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 all done. Right? Questions? So next step?
Would you recommend to use the command like a batch file to run everything at once, or do you prefer to
Let me stop this.